Okay, our next talk is going to be about cooperative perception of future cars with GNU Radio, and Augustus Vega is going to tell us about this.
Hey, thank you. So good afternoon, everyone. My name is Augusto Vega. I am a researcher at IBM T.J. Watson in New York. It's my first time at FOSDEM. I am finding this really exciting. As far as I have seen, the talks are quite technical, so I don't know if I will be that technical, so hopefully you will still find something of interest today. This is about a cool project that we are doing in the context of, in general, connected to what Dr. Better was referring to before, heterogeneous chips, heterogeneous architecture, but I will talk about the application that in our case is driving that, which is cooperative perception in connected autonomous cars using radio. So very quickly, thank you very much to all the people involved in this project, my IBM colleagues, as well as our university partners, in particular students, postdoc, who are doing amazing work. Also, thank you to Dr. Tom Rondeau, who is the program manager of the DARPA DSOC program, under which we are doing this work. So the talk will be organized in this way. I will start very briefly describing this EPOCS project that we are at IBM leading with the university partners, and a little bit about, this new era of heterogeneous chips, right? And then I will go from that broad, let's say, a concept to more specific into one piece of that project, which is this EPOCS reference application, or ERA, which is about cooperative perception in vehicles. And then I will focus on something even more specific, which is one element in that application, which is the AO2.11p DSRC transceiver within ERA, and some optimization and acceleration opportunities that we have identified so far, right? So let's start saying that in 2018, DARPA started this program called Domain-Specific System on a Chip, the SOC, right? Which ultimate goal is to develop a methodology that allows us to build heterogeneous chips very fast for an application domain of interest. In this case, when we say a domain, it's not just a single application, it's more than that. Actually, we talk about the superdomain of embedded processor for autonomous connected cars in our specific EPOCS project. More specifically, we say that that application is for cooperative perception, including elements that come from the domain of computer vision and as well as software-defined radio. This is why we talk about a domain and not one single application. Right? So what is cooperative perception? First of all, this is not a term that we have invented, right? Many car makers are talking about this today, but the idea is simple. The way automakers have been evolving, advancing cars, connected autonomous cars so far, is by making a car as intelligent and powerful as possible, by putting more sophisticated sensors and more capable computation engines on board, right? We try to make the car, let's say, self-sufficient, right? But still there are some limitations to that approach. For example, I like this simple example, right? There is a car trying to do object recognition, and the car correctly detects two other cars in front of it, but it's also detecting some bicycles and also a person. But if we look carefully, these are just a decal, which is stick to the back of the car in front of me, right? This is a misclassification problem, pretty common in vehicles today. So clearly, if we keep doing a car very, very powerful, there may be still some of these problems that we need to think a little bit harder how to fix. So what we like to study, or let's say to propose, is this complementary approach of multi-vehicle cooperative perception, where cars can very closely interact with each other, right? In addition to doing its own stuff, a car can interact with each other to resolve, for example, this kind of ambiguities in real time while they are driving an environment, right? Specifically, what we have in mind as part of this project initially is relatively simple. We want a car to create a representation of the world, right? In this context, in the form of two-dimensional occupancy maps. A car will create these 2D occupancy maps with information about the presence or absence of obstacles in the surroundings. And these cars will exchange this map in real time, right? And will, more interestingly, will fuse all these maps together. I mean, a car will have its own representation of the surrounding and will receive other maps from other cars. And we'll try to fuse all these maps together to have a more precise, more accurate, let's say, vision of the world, right? So this is what we are doing right now in the current version of the open source application that I will introduce. But in the longer term, what we want to explore is something that we call adaptive swarm intelligence. It's more like a more swarming, more complex than just exchanging plain raw data. We want cars to eventually learn from each other, right? Exchange knowledge, right? Think of that sort. But in general, what we believe is that the number of false predictions while a car is driving can be significantly lower by benefiting from these swarm-based cooperative approaches compared to the car-centric only approach that, let's say, car manufacturers are following today, basically. So this is the motivation of why we started building this application. So let me very quickly say 2 words about the Epochs project, which is our IBM-led, let's say, solution for the design challenge presented by DARPA's DSOC program. So as I said, it's not just about the application, it's about the methodology that will take an application domain of interest, in our case from the domain of connected autonomous vehicles, and it involves, let's say, a series of steps to generate the underlying SOC, heterogeneous SOC, that we need to execute that application while meeting some metrics, performance, throughput, power efficiency of interest, right? So it's about the methodology, and there are many steps involved. We are developing an advanced compiler as well as a scheduler. We are also studying some mathematically grounded ontology generation mechanisms to more or less automatically identify what are the pieces of your application that are worth being accelerated in hardware, right? Instead of doing that like brute force as we usually do, we need something that is more mathematically grounded, right? So this is the ontology generation part. Then we have more hardware-related steps, for example, the design of accelerators, NOC, memory architecture for that specific, for the hypothesis generated by the ontology. So the ontology tells, well, these are the kind of part of the software that you should accelerate. So then we need to determine what accelerators we need, how do we connect them, and what kind of memory system we have to put. Then we implement. Initially, implementation in our case is just FPGA prototyping, but we need to also tape out this chip at least a couple of times to generate the final SoC. So Epochs is about the methodology, but today I will just focus on the application, right? Also, to give you a little bit of context, this is something actually that Dr. Vetter presented in his presentation before. This is the full stack that is being addressed as part of the DSOC program. This presentation is just about the application, right? Later on today, I will be presenting something about the scheduler also, and I will be touching this other layer here, the operating system. So let's go into the interesting part, the Epochs Reference Application, or ERA. So ERA is an open source application available in GitHub that basically implements this idea of cooperative perception in connected autonomous cars. And there are 2 important parts in ERA. One is the communication fabric, and the other is the sensing fabric. So communication fabric, as you can imagine, is all about communication, in this case between vehicles, vehicle-to-vehicle communication, B2B, using DSRC new-ray implementation of the AO2.11p protocol. So that is the top box in this diagram. And then we have the sensing fabric, which is about collecting sensor data from the sensors in the car, right? And generating this representation of the surrounding, which in the current version of ERA is a two-dimensional occupancy grid map, right? So then these 2 things work very closely, because in this way we allow a car to generate its own map and receive other maps from other nearby cars and fuse all these maps together in real time to have a better vision of the surrounding, right? So this is an idea in very general terms. So ERA involves multimodal sensing, although today mostly is a camera sensors. It involves the generation of local occupancy grid maps. It involves DSRC-based vehicle-to-vehicle communication, and final real-time fusion of those maps. So in the current version of ERA, version 2, available in GitHub, we are using a simulator called Gazebo. I don't know how many of you are familiar or know Gazebo. Raise your hands. Okay, so Gazebo is a pretty detailed physical simulator for robotics environments. So this is what we are using in the current version to simulate an automotive scenario, although our cars in this case are robots, and our streets in this current version is just a simple 3D world where this robot move around, basically. We will change this in a future version of ERA. So we have Gazebo, where we have this robot with these depth cameras attached, collecting information from the world, right? So this is our world simulator. Then we have a block called COSMAP2D, which is part of the robot operating system, ROS. How many of you are aware of ROS? A little bit more. Okay, we are getting close. So ROS is it's not an operating system by itself. Actually, it's just a robotics software infrastructure that provides many libraries to build very quickly robotics applications. So we are using one of its available modules, which is a COSMAP2D block, which allows us to generate these two-dimensional occupancy maps from data collected from the depth camera in the robot. So we generate in real time, many times per second, these 2D maps. And then, by the way, I mean, it's not just about the 2D map is not just about the presence or absence of blocks. It's also about what those obstacles are. So we also do object recognition, right? We want to label also those blocks. It's not just, okay, there is something there, but we want to know that if there is another car or a pedestrian or a tree or whatever, right? Then we take that and we pack it, we serialize it, and we inject it in our GNU radio transceiver, which, by the way, this is an open source implementation by Bastian Broesel. I think 99% of you know Bastian very well. So we took Bastian's implementation of the AO2.11p transceiver, and we integrated that into ERA. So this is where we are using a GNU radio. And this is interesting to mention that we have like two disparate worlds coexisting here, which is GNU radio and more ROS Gazebo, right? So we had to build like a ROS GNU radio interface to allow these two worlds to coexist, right? So I think that was something pretty interesting. And finally, we will also receive other maps from other cars through the GNU radio receiver. So what we want to do is to unpack that map and to merge together, to fuse together the locally generated one with the remotely received ones and provide the final version. This happens several times per second, by the way. It's very CPU intensive, right? There are two ways to execute ERA today. One is two-computer setup, where you take ERA and you deploy it in two different computers, and you have over-the-air communication between both of them. For that, you need, of course, USRP devices. So the other easier way to execute ERA is in a standalone mode, where the two, let's say, instances of ERA run in the same physical computer, so the communication between both of them will be using a regular network socket, right? But functionality-wise, this is the same as having over-the-air communication, right? So probably this is the easiest setup to start with. So now let me go into a little bit some characterization that we conducted on the transceiver of ERA and some optimization opportunities that we have identified that may be of interest. So as I said before, ERA has several components. I will be focusing now on that box there, the vehicle-to-vehicle communication part, which is actually the AO2.11p GNU radio transceiver that we took from Bastian, right? So when you take a software that you don't know and you want to identify acceleration opportunities, what is the first thing you usually do? Well, you characterize the application on a well-known system. So we took this transceiver, we executed it on some machine, right? And we start measuring the amount of computation cycles taken by different part of the, in this case, of this flow graph, right? So what we observe the very first CAD performance analysis is that there are actually like two functions, new radio functions, that are consuming most of the CPU cycles. These are the complex exponent floating point function, which takes more than 30% of the execution time in this current implementation. And the other one is the computation of the Viterbi butterfly, which is a little bit more than 10% of the overall execution time. So we say, okay, we have two candidates to optimize. Let's start with these two. And by the way, what are the parts in this flow graph that are making use of those two functions? And we identified these four blocks, which is packet decoding, OFDM equalizer, and synchronization, long and short. So these are the ones that are highlighted in red. These are the blocks that are making use of these two functions most of the time. And actually, the four of them belong to the receiver, which means that, well, the receiver is more critical, clearly is more critical than the transmitter, right? So, okay, we started with these two functions. Let's see how we can accelerate them and how much benefit we can get in return. So the first thing we did is, okay, we defined a CPU, a baseline, which in this case is a general purpose CPU, an ARM Core A53 processor, very, very basic stuff. And we measure, this is just for one of these two functions, for the complex exponent function. We measure, on average, how many cycles it takes to call that function. And in this case, was around 37 CPU cycles on average for the execution of this complex exponent function, right? Okay, so we move forward. We say, okay, let's design our own preliminary acceleration engine for this function. And the way this function works is very simple, actually. I mean, the computation of the complex exponent is a computation of an exponent multiplied by these cosine and sine elements there. So we say, okay, let's design a dual path pipeline where one part of the pipeline, the bottom one, will compute this piece. The top one will compute the cosine and sine and add them together. And at the end, we will multiply to generate the final result. So this was our very first version of our accelerator, right? Very simple one at the beginning. We had some issues that we had to deal with, like, for example, unbalancing between these two paths that we managed to fix. So we start measuring the execution time of this function using that accelerator. As expected, we managed to go down from 37 to around 7 CPU cycles per call, right? Which was a huge improvement. Of course, since this accelerator is, let's say, outside of the CPU, then we start having some memory copy overhead, right? We have to move the input data from the CPU into the accelerator and then move back the result again into the CPU, right? So this is our, let's say, first version, not very much optimized of the accelerator. Then we decided to try something also relatively straightforward. Say, okay, let's try to use a vectorized version of this function, right? And voila, the vectorized version took even less cycles than the accelerator, right? So around 5 or 6 cycles. So that was actually very interesting. Say, okay, we don't have to move data because this happened on the same CPU, on the same core, and it still performs better than our accelerator, right? But our accelerator was not very well optimized at the very beginning, so we start looking into some more aggressive optimizations. And what we realized is that, okay, I mean, in this case, the accelerator was running at 100 megahertz, right? So to be conservative, say how much we can increase that frequency. Well, we can go up to 300 megahertz without violating timing and things of that sort, which will provide us like 3 times speed up, right? Plus, we can have, for the silent board that we are using, we can have up to 4 copies of this accelerator running in parallel. So we have another 4 times speed up. And the most important thing is that we believe we can eliminate the memory copy overhead, because the memory copy overhead here is mostly due to the way virtual memory in new radio buffers is mapped to physical memory, right? So that mapping is changing all the time in radio, and therefore force us to keep copying data from one physical location to the new physical location where the buffer is mapped to now, because the buffer is actually rotating, right? If we could get into a new radio and fix that, then we could eventually ideally eliminate that extra memory copy overhead. And the result would be like each call of this function using this fully optimized version of accelerator is around one cycle per call, right? So significant performance improvement, right? Let me very quickly, because I am also arriving to the end of the time, but let me also quickly tell you what are our plans for ERA, because we need help, right? And we think this is very exciting. Connected autonomous cars. Who doesn't want to work on connected autonomous cars? Right? Don't answer. So the current version of ERA is version 2, available in GitHub, as I said, the one that supports this two-computer setup. We are going into version 3 of ERA, where we will replace Gazebo with a more realistic automotive simulator emulator, like, for example, CarSim or Carla. This is something we are trying to decide, right? But more importantly, this part of this diagram here, layer 1 and layer 2, is what we have today in terms of software platform for automotive. We have very good world simulators. CarSim, well, Gazebo can be used for automotive too. Carla and LGSBL are some examples. We have very good automotive platforms to implement perception, plan, and control in simulated environments or in real cars, right? But we don't have that piece there that enables vehicle-to-vehicle communication in this existing software ecosystem. So this is what we want to provide with ERA version 3. We want to create the missing part here, which can interact with layer 2 and layer 1. And if a user wants to have, in a very easy manner, support for vehicle-to-vehicle communication, regardless if she or he is using, let's say, CarSim plus Apollo or Carla plus AutoWare, right? So this is what we have in mind for ERA version 3. ERA will be only intended to enable cooperative automotive with support for DSRC, currently supported, and eventually in the future 5G, right? So this is what will make ERA unique, right? And we need help for that. So to wrap up, I think we all agree that the domain-specific heterogeneous SOC ERA is here, based on some talks that we have already seen. This is because we need to significantly improve performance throughput as well as power efficiency. DARPA understands that very well, and this is why one of its programs, the SOC, is about heterogeneous SOC. So under this SOC, we are developing this open source application called ERA for multi-vehicle cooperative perception that includes, as I said, local sensing plus vehicle-to-vehicle communications in the same application. In other words, ROS, the robot operating system, and new radio can coexist together if at least based on our experience, right? The SRC plays a critical role for vehicle-to-vehicle communication, right? If we want to have a world where cars can interact with each other and swarm between them to exchange not only raw data, but also, let's say, knowledge, experience, then we have to focus on how those cars will communicate in real time, right? High throughput, low latency, right? So we have to put the focus on how do we accelerate that. And finally, as I said, we want to turn ERA into a benchmark for cooperative mobility that can be easily plugged into existing automotive platforms. So if you want to collaborate, please reach out to us, to me. Check out ERA in GitHub too. So that's it. I don't know if there are questions.
I'm driving OpenPilot. I'm driving autonomous car based on OpenPilot and other open source software. Do you, in your to-do list, have implementation of your project in OpenPilot? And what kind of protocol you use in order to communicate between cars, like MapLink in UAV world? Do you have a standard for the communication between the cars?
So the question was, first part was if we are considering autopilot when we talk about ERA version 3. I think the question is, in this figure, do you have a box that is autopilot too, right? In addition to Apollo or AutoWare, right? So, I mean, the way we want to build ERA version 3 is independent of anything else. we want to actually define some APIs that can work with eventually any other infrastructure, let's say Apollo, AutoWare, Autopilot, or whatever, right? So it should be extensible in that regard. So yeah, I mean, the answer is yes. In the future, we can also include Autopilot in this diagram. And the other part was about the communication, the protocol between cars. That is actually a very key question, right? And something that we are investigating as part of this project, right? How do cars communicate to each other? For now, it's just we take these maps, we pack them, we compress them, we serialize them, and we exchange them in very simple manner. But we need to define a protocol, and MapLink may be one option. Yeah. So.
I've got one really quick question.
Yeah.
How big are the buffers you're copying in and out of your accelerator?
You mean the buffers in between new radio blocks?
How big is the GNU radio buffer feeding and taking data from your accelerator?
I don't remember the number. Let me check it out.
Yeah, I'm curious.
Yeah, because that changed many times already. But
it's going to depend on how.
yes. Let me check that number. So I think there is one more.
Megabytes or kilobytes?
It is in the order of the kilobyte.
Okay.
Yes,
Kilobyte.
yes,
That's a
kilobyte.
good number.
Yes,
That's
yes,
good.
yes. Yeah, security is key here. Actually, something I didn't mention, we are also moving from ROS 1 to ROS 2 because ROS 2 provides some security features that we will leverage in ERA version 3. We believe that, in general, swarming can help us to identify like some, let's say, adversarial cars in your swarm, right? For example, running some real-time consensus mechanism in real time, the cars can say, well, that guy here is being robbed, all right? So we should probably take him out from our swarm right now. So, but it's a very key part. DARPA is very interested in that, IBM also, so we are looking into that. I don't have an answer, but swarming may be probably one of the ways.